All right, so this is going to be as quick as I can possibly make this on solving rational inequalities. And the thing about solving rational inequalities is that you don't actually go through a solving process, and I'll explain that on the next slide as to why you do not. Um, but what you do is actually you do something called sign analysis. And sign analysis is this idea that basically if you have some function and you're saying it's greater than zero, then that function will have to be positive. So the outputs of that function have to be positive if they're greater than zero. If they're not, then they're not greater than zero, and we can say that that's a contradictory. Okay, if something contradicts, then it's not true. So what we're going to go off with is this sign analysis so that we can pick and point out which points are actually, or what portions of a domain are actually part of my final answer. And the other part of this is that if I have some function, I'm saying it's less than zero, then that function must be negative. So that is an extremely, this piece right here is an extremely important idea that we kind of have to solidify, that this piece right here, that's extremely important for our sign analysis. So basically, I just wrote here to solve rational inequalities, we use sign analysis because using a mathematical process cannot weed out extraneous solutions, nor does it pick up any, nor does it pick up some solutions that are actually solutions based off the mathematics that you're doing. So to demonstrate that, I have a rational function, and the rational function I have is this x plus 3 divided by x minus 5, and I want to know when is this thing less than or equal to 4. And over here to the right, so this is the actual graph of it, okay, this piece here is the actual graph of your function. Now, a couple things I want to point out is that, if you're talking about rational functions, you're probably in an Algebra 2 or a pre-calc class, hopefully. So what I'm about to talk about, hopefully you'll have talked about previously. But right now, domain-wise, if you notice in a fraction, okay, you can't have the denominator be 0. If the denominator of a fraction is 0, what that actually creates is an undefined function. So when you have a leftover function and it has a expression in the denominator, those values, whatever they are, will create these things called vertical asymptotes. So what I have right now is a vertical asymptote at 5. And if you see this graph here, it kind of looks like it goes up to almost where it's getting to 5, and then it starts veering off. It's like, oh, no, heading towards 5. Let me get away with it. And then the other side, kind of the same thing. As you head towards 5, it kind of just veers up. So to show this very quickly, okay, what I actually have going on is this vertical asymptote right at 5. So I've got this straight line coming in, all right, that essentially is just going to be a vertical asymptote. So I'll draw this here down in red, okay, so this dashed line, what you can see, all right, is that I have this vertical asymptote. Now, also, if I have a function, okay, just going a little bit more in depth, okay, how you would figure out a horizontal asymptote. And a horizontal asymptote is you would look at your rational function itself, and you would say, okay, the exponent of the degree of the numerator, is it less or more or equal to the degree of the denominator? If it's equal to, you divide their coefficients, and that is where your horizontal asymptote lies. Okay, and in this case, that's all I'm going to stick with. I'm not going to go too far into this. This video is not about how you find out horizontal asymptotes. But notice that the degree of x plus 3 is 1. The degree of x minus 5 is also 1. So what I would do is I would take the coefficients of 1x and 1x and I would divide them. So 1 divided by 1 is 1. So what I have here is, you can also kind of see on this graph now, is I've got a horizontal asymptote, okay, that goes across. So what I got going on here are these two things. So what this graph has, all right, is extremely, extremely important, because the way that this graph is formed actually, okay, will for whatever reason it won't pick up when we do the mathematical process. It won't pick up the bottom half here. So when we go through and do the math piece of this, it actually doesn't even take this piece into effect, because if you follow a mathematical process that I'm going to show you in a second, I just want to show you what happens and what you turn this into. So right now, this is a rational expression, and all rational expressions have this kind of thing going on where you have a vertical asymptote, or maybe even a horizontal asymptote. Doesn't have to be both, could be one or the other. and you have this graph, okay, that kind of looks like this boomerang looking thing on either sides. So what I want to show you very quickly is that if I were to solve this like a rational equation, all right, and you were to do the cross multiplying bit, let's take a look at what happens, okay? So if I were to solve this like normal and I were to say, okay, multiply both sides by x minus 5 by x minus 5, what I want to point out right now is by doing that, you are now getting rid of the rational expression. So what you now have is this thing of x plus 3 is being less than or equal to 4x minus 20. And what is important here is that once you change it out of a rational expression, you are losing properties. And once you start losing properties, you start losing solutions. And that is why we cannot and should not ever, okay, get rid of that denominator. That denominator is extremely important because if you get rid of that denominator, effectively what you have done is you said that this vertical asymptote here does not exist anymore, and clearly that vertical asymptote exists. So you do not want to solve these like their equations. Do not do that piece. I don't even need to go any farther than this because all I want to point out to you is that if you start solving inequalities like equations, you will lose mathematical properties. So if you don't solve them like equations, well, then what do you do? And I'll show you what you do. You do this thing called sine analysis. Okay, so I'm saying it's less than or equal to 4. So sine analysis means is that you're going to go in, and what you're going to do is instead of saying that you have some function, so right now I have some function, and I'm saying f of x is less than or equal to 4, okay? Well, the problem is that to be less than 4, I could be a positive or a negative number. There's some ambiguity there. So what I actually want to do is I want to go back to that idea where I had in the beginning where we're talking about f of x being less than or equal to 0. So what you want to do here, okay, so you can solidify your answers, is you actually want to take this 4, all right, and you want to move it over here, and then you want to create one rational expression. So when I move it over there, I get this new expression of x plus 3 divided by x minus 5 minus 4 is less than or equal to 0. So now I'm starting to get this thing less than or equal to 0, but right now I don't have a function. I have two things being subtracted, and to be a function, I just need one expression. So the one irrational expression that I want, I need to combine them. So to do that, I need to make common denominators. So the denominator here is x minus 5. I need to make the denominator of 4 over 1 into x minus 5. So I simply multiply it by the quantity of x minus 5. Now, you just have to be careful because when you multiply top and bottom by something, okay, you must multiply both equations. So I'm going to multiply this by x minus 5 and the denominator by x minus 5. And what that now creates is this new expression of x plus 3 over x minus 5 minus 4 times x minus 5 divided by x minus 5, which is less than or equal to 0. So what I'm actually doing here is I'm actually combining and simplifying. I'm not actually going to solve. And then we're going to go back this. So now I'm going to combine them. Okay, so this becomes x plus 3. And if I do the distributive property here, don't forget your little negative here. It's negative 4x, so minus 4x. Negative 4 times negative 5 is positive 20, divided by x minus 5 is less than or equal to 0. So simplifying the top, again, a little bit more, I get negative 3x plus 23 divided by x minus 5 is what's less than or equal to 0. Now, from here, I need to figure out intervals of values to test. So one interval, if you notice, like just looking back at this graph, one piece of interval I'm going to test is what happens if my number is greater than 5. So what I want to do here is, in this function, I want to create these things called critical values. And these critical values are, well, I know right now that x cannot be equal to 5. And that's a critical value because that separates, okay? That separates, if you look at this graph, all right, that is separating my function. So I have the right side of the function and the left side of the function. So right now, the right side of the function, all right, looks like it's greater than 4, but this whole thing isn't necessarily greater than 4. So just to show that, this is 1, here's 2, here's 3, here's 4. So basically what I'm saying to you is anything less than this, or greater, any x value greater than this point here is going to be less than 4. All right. So, however, it doesn't mean anything less than it is always greater than 4, because look what happens down here. So we're going to talk about that. So we also are going to figure out what is the exact value that will actually give me 0. And to do that, the numerator must be 0. So down here, I figured out what was the 0 of this. So 5 minus 5 made 0. That made it undefined. So at the top, I'm going to figure out what makes this into 0. So the way that you do that is you take the opposite of this number, so that's negative 23, and divide it by that number, which is going to be negative 3. So negative 23 divided by 3 is 23 over 3, and 23 over 3, so if x equals 23 over 3, which is 7 2/3, that's when I will get this function that will be equal to 0. So what this now has me is my critical values. And what we are going to do is we are going to do sign analysis surrounding these critical values. Okay? So what you do is you make a number line. So here's my number line, and you're going to plot these critical value points. Now you make sure you got to have all your critical values. So I don't have a lot here, but this is it. So my first critical value is 5, and my next one is 7 2/3. Okay? So what you're going to do is sign analysis. So right now what you need to understand is that this function right here that I'm boxing up in red is my f of x. Okay? So I want that function to be less than 0, which means I want whatever numbers I plug in to produce negative numbers. If they produce a negative number, then that means I am good to go. All right, so that's an extremely, extremely important piece, okay? So now, looking at this graph, now you're not always going to have a graph, but I want to show you something here. Looking at this graph, if I pick a number that is less than 5, all right, so say like 4, and I plug it into this function. So if I do 3, so I'm going to squeeze this up a little bit here. If I do negative 3, okay, so I'm plucking 4 off of this piece here. So negative 3 times 4 plus 23 divided by 4 minus 5. Now that becomes negative 12 plus 23 is 11. 4 minus 5 is negative 1. 11 divided by negative 1 is a negative number. So the sign to the left of 5 is negative, which means it is less than 0. That is extremely important. My sign analysis is proving to me that numbers that are x values that are less than 5 are going to fall underneath the value of 4. Now, what I'm just showing you here mathematically that I just proved by picking a point off of here is notice that this side here is the value of x being 5. Anything on this blue graph, okay, I am saying to you will always produce a number less than the 4, okay? So here's 4. Anything on this side of the graph will always be less than 4. And I mean, if you look at it, it's true. We have a horizontal asymptote going across, which means this thing will actually never even be greater than 1. So therefore, since it will never even be greater than 1, it will always be less than 4. All right? So just to show this some more, all right, pick a number between 5 and 7 2/3. So I'll pick a number like 6. So I go ahead and I do sign analysis, which means I plug it in, and I'm just going to check, is the answer positive or negative? If it's positive, I want it to be negative, which means it doesn't work. So we go like this. We go negative 3 times 6 plus 23 divided by 6 minus 5. So negative 3 times 6 is negative 18 plus 23 divided by 1. Negative 18 plus 23 is positive 23. It's positive 5. 5 divided by 1 is positive. I don't care about the number. I care about the sign. So it's called sign analysis, which is a positive. Well, I don't want a positive, okay? That means I'm actually greater than 0, not less than 0. So then I continue on with this sign analysis thing. I'm going to pick a number, not 7 2/3. I'm going to pick a number that's greater to the right of that. So I'm going to pick a number in this range here. So before I pick 6, okay, so numbers I picked are 4, 6, and then I'm going to pick a number that's greater. So I'll pick 8. Okay, it doesn't matter what you pick as long as it's greater. So 3 times negative 8 plus 23 divided by 8 minus 5. And all I'm doing is plugging these numbers into my f of x that I said that I simplified to. So 3 times negative 8 is negative 24. Negative 24 plus 23 divided by a positive 3. So I get negative 1 divided by 3, and that is a negative number. So what I have here is I have intervals, okay? And the intervals I have here, you can see, is that if I am less than 5, okay, that means I am, all right, going to be less than 4. And also simultaneously, as this function gets greater than 7 2/3, it will also be less than 4. So what's extremely, extremely important here now is that we have one tiny little thing that we have to do. So what we do is we go back to our critical values. So our critical values here, okay, they're going to decide whether I have an open circle or a closed circle at my critical value. So what I got going on here, okay, is that x cannot be 5, so that's an open circle, okay? And then what I will do is I will say anything in the region left of 5, okay, is part of my solution. And I go to 7 2/3, it is equal, so that is a closed circle because that's going to produce 0. Anything to the right of that is part of my also solutions. So just to go ahead and show you this very quickly, that if I went to up to 4, the outcome of 4, that number right there is the coordinate pair 7 2/3, comma 4. Okay, so that's an important piece because what I'm basically showing you now is that anywhere, okay, below that line, it would be less than 4. So anywhere on here has an outcome, a y value that is less than 4. All right, and anything on this part of the graph, okay, also has a y value less than 4. So what we have is a tiny interval between 5 and 7 2/3 in which the function is actually greater than 0. Here you can see it in blue. So the sign analysis helps us prove that. All right, so which is why we do not want to solve this. We actually want to simplify it into one rational expression. And after you simplify into one rational expression, you want to do sign analysis. All right, so I hope that helps with whatever you're doing.